Okay, so we made it to our third important subcortical supratentorial structure of the brain, the basal ganglia. What we see right here is the caudate nucleus and the putamen put together, which is collectively known as the striatum, which is going to be a really important central player in the basal ganglia pathway. So here we're just looking at a sagittal slice. I'd be kind of familiar with it. It kind of looks like a headset or, a Mewtwo tail. And I would also know the coronal slice here. So here again, we have the putamen with the globus pallidus, both the externus one on the external side and the superficial side, and then the deeper internal one. The caudate nucleus is up here. The thalamus is kind of in the center of everything. And then we have the substantia nigra. So I just think of like sub being below. And then the substantia nigra really actually just means black substance, which is why this is kind of dark. And that's because tyrosine, derivatives of tyrosine are neuromelanin and dopamine are part of the same sort of pathway. So you have a lot of dopamine here, and you also have a lot of neuromelanin. Now, in between the thalamus and I guess the lentiform nucleus, which is these two together, we have this internal capsule where we're going to have a lot of axons moving, from the brainstem and the spinal cord up into the cortex, trying to get to the gray matter cell bodies up here. Here's a better picture of the internal capsule. And in my opinion, the lentiform nucleus kind of sort of looks like a candy corn. So that is just to illustrate what a horrible artist I am. That's something I drew. All right, so let's go ahead and watch this dumb video. All right, so here's the thalamus, caudate nucleus, putamen. Okay, here's GPE, GPI, substantia nigra, that's dark, and then the subthalamic nucleus. And here's everything just kind of labeled again. And all right, so we've said before, the caudate nucleus and the putamen together is the striatum. This is probably the more important name to know because that I guess that's a more cohesive from a functional perspective than at least as far as my dumb brain understands, than the globus pallidus, externus, internus, and the putamen makes the lentiform nucleus, right? Like this looks more cohesive, but I think actually from a physiological perspective, we'll refer to the striatum more than we will the lentiform nucleus. All right, watch this. Watch. Boom. All right, now watch it in slow motion. Oh, that's pretty cool. That's slick. All right, so the whole idea is that when your brain is trying to it says, hey, we want to do a handshake. We want to do some sort of, greeting. That your cortex wants to do this, right? And it then is going to communicate with the basal ganglia to say, hey, like, what's the best way to make this happen smoothly? And, there's so many different ways that we can shake hands, and, it's your basal ganglia that's kind of modifying this very dumb, rough draft that your cerebral cortex does, yes to certain muscles being activated, no to other muscles being activated. And that is partly what was going to help the finished product of this, just like terrific, very precise motor movements. Boom, amazing. Can never get tired of watching that. All right, so my it's really complicated. So my dumb analogy involves Game of Thrones. If you haven't seen Game of Thrones, that's fine, because if anything, some of this is going to be spitting in like Game of Thrones, like the mythology, the lore. But the cerebral cortex is the king. They want something done, and they don't really. I want to move my hand. Like, how should I do it? So the striatum is like that's the advisor they go to tell, hey, I want to move my hand. How should we get this done? The striatum is wise, and it's this is the striatum. The striatum is wise, and it's going to try to help the king. As dumb as the king is, it wants to get this done, and it's going to help try to coordinate, turning on and off different systems to get this done in the best way possible. Now, the last end of the road is the thalamus. The thalamus is the king's yes man. His goal is to always say yes to the king no matter what, because he's been around for so long. The king's always going to listen to him. So sometimes we're going to have to shut down the thalamus because the striatum says, well, the thalamus is an idiot, and we don't want to say yes to the king's request. The GP, globus pallidus, internus, and externus, I think I for inhibit. So the GPI and the GPE, they are immediately inhibiting the thing that they're always connecting to. So immediately one step downstream, always an inhibition. And I just think of them as dumb warriors, and all they know how to do is like break stuff and inhibit things. But ultimately, these are actually very different players. The GPI ultimately wants to inhibit movement, so it will inhibit the thalamus, which is trying to say yes, let's do this movement, king, sure, whatever you want. And then the E is actually trying to agree with the thalamus, and it ultimately wants to E for excite movement. Also, whenever we're inhibiting something, we're using GABAergic neurons. And then the subthalamic nucleus, I think somebody who's been under, subthalamic, that's because from an anatomical standpoint, it is right under the thalamus. But I think of it as like it's under the oppressive rule of the thalamus, and it's had enough. It wants to rebel. It wants to shut down the thalamus. All right. So the king says, I want to pick my nose. Which finger should I use? And it's going to consult the striatum, and the striatum wants to is as much of a jerk as the king is. It wants to help the king, so it's going to initiate a bunch of different things, turning on and off things to help this happen. Now, again, the thalamus is just a yes man, and it ultimately is like the last in line to talk to the king, and so it's always going to say, yes, that's a great idea, my lord, we should use the pinky finger or the index finger or whatever you said, I agree with it, right? And so the striatum's like, the striatum's actually the smart one saying, I don't know if that's a good idea. So it might have to, let's say it's 50-50, sometimes the king is right, we should do this, and the thalamus is activating, we want that. So then the striatum wants to say, okay, yeah, that's sure, I'll let the thalamus activate it because that's the right course. And other times the thalamus, it's a dumb idea, and the thalamus is saying yes, but the striatum says, no, that's actually a pretty stupid thing, we shouldn't do that. So it'll then want to turn off the thalamus. So it's inhibiting these brutes, it's saying, hey, all you guys know how to do is just break stuff, like stop it. So the striatum is just not, it's not for big brutes and violence. So it's always trying to inhibit the GPE or the GPI, no matter what. That is it immediately what it is contacting with. The GPI's end goal is to inhibit. So that's easy. The thalamus is trying to activate always and forever. So the GPI is just going to achieve its goal by inhibiting the thalamus. Now, the GPE's goal is ultimately to excite. So a way to do that is to interact with something we don't know, turning that off, which is turning on the GPI, right? So, and if we just think about like double negatives, here's one negative and two negatives, that is going to be an activation pathway. And here I have 1, 2, and 3. 1, 2, 3. 1, 2, 3 wrongs kind of like is going to make a wrong. It's going to turn it off. So 3 negatives makes a negative, 2 negatives makes a positive. I promise this will make more in a hot second. All right, so the subthalamic nucleus is just like, I'm tired of your shit. I'm tired of being under your oppressive rule. I want to turn you off. But this person right here is a coward. They can't do it directly, so they need to go through somebody else to turn off the thalamus. So they're going to, kind of get this mercenary, this swordsmith, to this big brute. They're going to pay them to shut down the thalamus. And that also makes sense, again, because the GPI's job is to inhibit movement, and the thalamus is trying to activate movement. Okay, so the direct pathway, the king, we want to scratch a nose, and one of the king's ideas is, hey, should I like flex my index finger to scratch my nose? And yeah, if you want to scratch your nose, like flexing your index finger is probably like a useful thing. So the king tells the striatum, I want to flex my nose, and so the striatum says, let's do the direct pathway. It is going to inhibit the brute, the GPI, which is inhibiting the thalamus, because remember, this is always trying to... the GPI is trying to inhibit movement, but if the striatum inhibits it, boom, you get movement. I was just thinking of like 2 wrongs make a right. Again, green is glutamase activate, red is GABA, which is inhibit. And so, boom. So do we want to flex our nose if we're going to scratch our nose? Yes, that is actually a smart course of action. All right, what if we, the king says, hey, should I flex my pinky finger? I don't know, you could, like, to each his own, but I don't think you're typically going to use your pinky finger if you're scratching your nose. So the striatum is like, that's a terrible idea. Like, that's not at all what we want to do. So it's going to set in motion this cascade to ultimately inhibit the thalamus, which is, again, just a yes man, always not even thinking. The thalamus doesn't think, it just says, yes, king, whatever you want, and the king will listen to it. But we want to shut down the thalamus because the striatum, the wise one, knows that's actually not a good idea. So it is going to inhibit this person who's, again, what are they trying to do? Their end goal, whether or not they're doing it, their end goal is to excite. Now, they're not doing it because they're being inhibited by the striatum. They are a brute. All they know how to do is inhibit. So they inhibit the subthalamic nucleus. You remember, the subthalamic nucleus hates the thalamus because it's under the oppressive rule of the thalamus, but it's a coward, so it doesn't do it directly. So it goes to the GPI, whose end goal is to inhibit. And we have 1, 2, 3 negatives, that makes a negative. 3 wrongs make a wrong. We're going to inhibit the thalamus. We do not want to flex our pinky. So again, pinky is not flexed. And again, the direct pathway says we will flex our pointer finger. Also, just note that the indirect pathway is a bit longer. Okay, now that's and that's the simple version, believe it or not. It gets more complicated now with this substantia nigra. Now, technically, we've had, I put it in small here, this is the substantia nigra reticulata. There's actually two parts to the substantia nigra. And it's really not that important. It's always just doing the same thing as the GPI. So whenever we say GPI, technically the SNR is also doing that as well. But okay, so now we're looking at the substantia nigra. And again, we have the reticulata, RET, for retarding. It's retarding movement. It's trying to inhibit movement with GABA. And then we have the compacta. And I think of compact disc, like a compact disc, a CD, and the D for dopamine. And, the tyrosine derivatives are dopamine and neuromelanin. So the substantia nigra, at least the compacta version, because this is the reticulata and this is the compacta. The compacta is going to be the dark part. And so the substantia nigra, I think, is this kind of two-faced individual. One of the faces is the reticulata, and the other face, and the reticulata is typically trying to retard movement, and the compacta is going to be trying to activate movement technically. So it's kind of doing different things, but they're also working in very different ways. So the substantia nigra compacta is what we're talking about now. Again, this is just not that important. It's just doing the same thing as the GPI. So the end goal is always going to be activation for the SNC. So it sends dopamine, and they bind to dopamine 1 receptors, which are green for activating. And so all green is glutamate except for the SNC, which is going to be dopamine. So it's activating this whole direct pathway. So it's just amplifying. It's just amplifying the direct pathway. It is achieving movement that way. And it's the two-faced one. Again, it's always, the end goal is activation. So what if we're trying to do the indirect pathway, which is to inhibit movement? We're still sending dopamine, but now they bind to D2 receptors, and D2 receptors are for inhibition. So now we're inhibiting the striatum when the striatum is trying to do the indirect inhibiting pathway. And if we inhibit that which inhibits, we're going to go crazy here with all of these double, triple, quadruple negatives. We are now going to, we have 1, 2, 3, and 4. 4 negatives makes a positive, means we're going to have activation. It is trying to stop the indirect pathway and it's trying to activate the direct pathway. All right, so without all my dumb metaphor, this is just what we should know. The cortex wants to get something done. It asks the striatum, which is the caudate, and the putamen. And the putamen has two options. It can go the direct pathway over here, and it is going to inhibit the GPI and the SNR, which is inhibiting the thalamus. The thalamus is a yes man. It's always trying to activate the cortex. Alternatively, we could have the caudate, or the striatum go to the GPE, which is inhibiting the subthalamic nucleus, which is trying to activate the GPI and the SNR, which is again trying to inhibit the thalamus, which is trying to activate the cortex. So again, it's really just whether we have 2 negatives or 3 negatives. 2 negatives means we activate, 3 negatives means we inhibit, in direct versus indirect. Now the substantia nigra compacta, not to be confused with the reticulata for retarding movement, is trying to always activate. So the D1 receptors will activate the direct pathway, and the D2 receptors will inhibit the indirect pathway. All right, so in genetics and in undergrad, if you knock out a gene, you get to see what the effects of that gene are, right? And it's the same thing here with the brain. If we take out a part of the brain, like Phineas gauge, we get a better idea about what that part of the brain does. So we can ask, what happens if the cortex dies? You probably can't initiate movement. What happens if the advisors dies? Well, it just depends on which advisors we're talking about. So 3 common ones: hemibalism. So if you go ballistic, it's kind of like you're moving a lot, and we get this hyperkinetic movement disorder, which you can see here. And so remember that the subthalamic nucleus is part of the indirect inhibiting pathway. And so if you're taking out part of the inhibiting pathway, you're going to get more movement, which is exactly what we see right here. Now, Huntington's is the striatum. Now, remember, the striatum is Peter Dinklage. He's a nice guy. He's trying to do just make the best course of action. So sometimes that's direct pathway and sometimes that's indirect pathway. But for the Huntington's, initially in the pathophysiology of the disease, it is going to be the indirect pathway first. Now later it's going to also inhibit the direct pathway. But again, initially it's the indirect pathway that's gone. And if we don't have the indirect pathway, that means we're going to have more movement. So that is why we are hyperkinetic, because we're losing the indirect pathway. At least initially. Later you're also going to lose the direct pathway. And remember that the striatum, Peter Dinklage, is always trying to say, hey, settle down, boys, you two brutes. And so it's inhibiting the GPE and the GPI, whether direct or indirect, is always inhibiting. So if we don't have this working, we're going to have less GABA. And if we have less GABA, and that means that substantia nigra compacta is not really being listened to, there's not going to be negative feedback that we need. So we're then going to get more dopamine because, again, the SNC is trying to tell the striatum what to do. And if the striatum's not there, it's just going to be classic negative feedback, the absence of negative feedback. So less GABA, more dopamine. If you think about it, it should settle. It should make sense. Parkinson's, we are specifically losing the substantia nigra compacta, right? The thing with the dopamine. And so if that's the case, remember, this is always trying to activate, right? It's activating the D1 with the direct pathway. It's inhibiting with D2, the indirect pathway. And so we're going to get hypokinetic or akinetic movement. So here we can see Parkinson's, not a lot of movement. Huntington's, we're seeing extra movement. And you should have less dopamine because you don't have an SNC in Parkinson's patients. All right, so nigrostriatal, think about the name, substantia nigra, that's the dark part, the black substance, the striatum, which is the caudate and the putamen. So this is going to be coordinated movements in the basal ganglia. Mesolimbic is going to be the VTA to the nucleus accumbens, and this is really just the reward pathway, the reward processing. So you get a positive symptom in something like schizophrenia. If you have too much activity of the mesolimbic system, you're going to have delusions. The mesocortical pathway is the ventral tegmented area, VTA, to the cortex, and this plays a role in regulating emotional responses to something. So if you don't have enough of this, then you're going to have a flat affect, where someone says, we have terrible news, your father has died, and you say, oh, okay. Or someone says, we have terrific news, you won the lottery, and you go, oh, okay, that's a flat affect. And the tuberoinfundibular. So we have an infundibular stalk for the pituitary system. And so that kind of is a hint. This is the hypothalamus to the pituitary. And this is going to be, it's weird. Dopamine plays a role in inhibiting prolactin. And so it's which plays a role in lactation.